It's episode 11. In this episode, we'll continue with our CPU test circuit, we'll add some RAM, we'll check out the circuit at full speed, and finally we'll model it in Verilog. So if we have a quick recap of what we've been doing the last few episodes, we put an image file into a ROM, as you can see on the screen here. It's got some messaging, Mr. Retro Wolf, Namco, and some graphics. Now these characters come from the Tank Battalion game, and we're just accessing those from the character ROM. So on the right hand side of the screen, you can see the memory area of the ROM that we're using, and we're putting specific character numbers into certain areas to get the characters that we want. In the last two episodes, we just implemented a simple circuit with just a ROM chip and a CPU, and the CPU fetched some screen data from a certain area in the ROM and wrote it to a virtual area of RAM. But of course we didn't have any RAM, so it was writing it to nowhere. So in this episode what we're going to do is we're going to actually implement that RAM. It's going to be called 0-page RAM because it's down in the low end of where the CPU sees. And we're just going to do the same test as we did in the last episode, whereby we'll write it to that RAM, but this time we'll also read it back just to check that it went in there as we want it to. Now on the screen it's just a reminder of the single line that we're going to check. So it's got a few characters there, the R of MiSTer, T of Retro, W of Wolf, a few numbers, and on the right hand side what those characters correspond to. So the bit of wall that we've got up there is 10 hex, we've got C2, C4, C7, and so on until we get down to that bottom wall which is 10 again. So we saw that in the last episodes, just a quick reminder there that's what we're doing. So this is the modified breadboard. This time, remember last time we had our CPU, and then we had our ROM. We had some logic there to select the ROM chip, but this time we've added two 2114 RAM chips. Now the 2114 is only 4 bits wide, so you see D1, 2, 3, 4. It obviously can't access 8 bits there, so we want an 8-bit wide data bus, so we'll just use 2 of those, and so those would be effectively D1 up to D8. So you'd make sure that it corresponds to the same data bits as here in the ROM, and also on the data bus of the CPU, and you can just connect those together. No problem there at all. So all the address lines are connected together, all the data bus lines are connected together, not going through any buffers. The other thing that you want to do is you'll need to connect the logic that connects those together. So we'll have a look at the schematic for that just to see exactly how that's implemented. Here's the schematic. It's been modified slightly from the last time. Previously we just had the CPU and the 2716 ROM. We've added the RAM, the 2114 RAM. So as said previously, we've included the data lines linked up to the data lines of the CPU and also the ROM. The other two important factors are the chip select and the read-write pin. So first, the chip select. We've got two chips we want to select with RAM or ROM. The A15 address line was, when it was high, was going to select the ROM chip, and when it was low, we wanted to select the RAM chip. So here, if it's low, we just come straight out and it's chip select. Remember, its enable is low, so we're good. If we're low on the A15, it will select it. If we're high, chip select is still low, so we need to go through a NOT gate. So that's what that's doing, going through a NOT gate if we're high on the A15. Now you'll remember from the last episodes that the ROM was replicated because it's only 2K, hence the same thing with the RAM, it's only 2K. It is replicated all the way up to 32K, and then after that 32K it's all ROM. So it will be repeated. Now for the test that we're doing, we're only specifically targeting two areas of ROM and RAM, so it doesn't really matter. But we can modify that if we need to, if we want a more complicated circuit. Then on to the read and write. It's just a straight output from the CPU into both chips of the 2114s. Active low for write, and for reading active high. And we had our slow clock and our debounce circuit again that we saw in the previous episode. Now, one thing that I didn't mention in the previous episode was that for these chips, we really do want to start implementing decoupling capacitors between the 5 volt and the ground rails. It takes away noise from the chips and makes them much more reliable. In this small circuit that we're using, it's not going to make a lot of difference, but I've already noticed on the larger circuit that without these decoupling capacitors, we really start to get ourselves into trouble. So that's what it looks like there. On the actual breadboard, I've just done jumper wires for this simple circuit. I put in a few different kinds of capacitor. I was just playing around with some different values. We've got some electrolytic, some tantalum, and some ceramic capacitors. The ceramic capacitors, 0.1 microfarads, are perfectly fine for this here. I also had a 1 megahertz crystal here and a reset switch on a separate circuit. I ended up not using this in the end. This was just a test. I went back to using the slow clock and the clock from the tank battalion larger circuit, since that worked just fine. Now, interestingly, what I wanted to point out was for the slow circuit, I did use the Arduino, as we had in the last episode or the time before, to measure the output of the address lines and the data lines. But I also am using a new logic analyzer called the Peritech Logic Analyzer. That's got 32 channels, so that's really useful because it allows us to look at the data lines and the address lines and read writes and clocks all at the same time. And then we can monitor how the CPU is operating with all of those lines to make sure that the program's operating right. So long story short, we can do what we did with the Arduino, but obviously that was really slow. That was just a couple of times a second on each clock cycle. We can go fully up to the 1 megahertz or actually much higher, and then do the same thing and make sure that the circuit is operating just fine. So when we get into then implementing the CPU in our tank battalion game, we'll be able to do everything and make sure that's all working still. And we're going to see in this episode some interesting points about when the CPU is working at the full speed, we maybe start getting into some issues with real world problems of reading from chips and possibly from breadboard circuits. So as you can see here, this circuit looks a bit of a mess now because we've got all of these probes on the CPU. It's a bit tricky to do this, but it's made a lot easier by using a special clip. This clip here is something you can clip onto the CPU. On the left side there, that clips over the legs of the CPU, and on the right hand side you can put your logic analyzer probes on the top, and it just gives a lot more space, and they're a little bit smaller than the legs of a CPU or any chip, to allow you to put a lot of probes on to a small space. So that's the CPU there, with on this side the address lines going from A0 up to A15. That ends about there. This is the ground, and then from there we've got the data lines D0 up to D7, and then we've got the reset line is that one, we've got the clock input is that one, and then this one is the read-write pin. So we're monitoring all of those at 1 megahertz so we can see how everything's operating. We've got another ground connected here just off that chip there. There's another closer look of the probes attached to the chip. Here's a different angle of the capacitors that we're just jumping into the circuit for the decoupling capacitors. And then here is the familiar two items. We've got this side here, we've got the reset circuit, and this side is the slow clock. So we've had to modify our program a little bit from the last time. You'll remember we had our circuit, we've got different kinds of addressing here. Now, one thing I did want to mention is there are some good sites to find more out about the 6502. We covered a few before. There's a good book called Atari Roots, which you can find online. This is a web version, and it just goes over programming the Atari 8-bit computer. And it's actually the same book as there's a C64 book. It's the same author. So they're covering the same ground, but it's just tailor-made towards the Atari 800 on this book. And it goes over some of the addressing modes. So we'll be familiar with some already. We'll have seen immediate addressing, and we also used the absolute indexed addressing last time to look in the ROM. We're going to be adding this one here in indirect indexed when we're actually looking at the RAM memory, and we're going to see that now. So just to go over again what the program's doing, so we are loading in 0 into the Y register just to clear that basically. Then we're setting up a loop where we're saying load A with the value in FB00 with the offset of Y. Now the offset of Y is 0 to start with, and then store that in the value of 200 with the same offset of Y. So again 0, so we offset into 0 into 200. And then we increment Y, and then we compare that value with 1F. And then if it doesn't equal 1F, we branch back to LL0, so loop 0. So what's that doing? If we look back in our diagram, we are going FB, and then we're going through these points here, gradually increasing. And then it's putting that whatever we find in this area into value 200 and above, or 200 hex and above in the RAM, and then later on we're going to retrieve that. So that loop happens, and then when we do finally get to the end of the line or near it, we then don't branch, and then this is a new part of the program. So this time again we put load 0 into Y, and now we're loading A with 02, and we're storing A into the location of 01, which is down in the 0 page memory. So we're storing that 02, and then we load 0 into the accumulator, and we store that in 00, which is the first memory location in RAM. And the reason why we do that is when we do this indirect indexed addressing, we pass it a value of the 0 page, which is kind of like a pointer, and it's going to retrieve an address from that area and one above it. So it's going to take 0100 and make that into an address. Now we've just fed into it 0200. So effectively this says load the accumulator with the value that's in 0200 with the offset of y. And we know y is 0, so it's going to find whatever's in 0200 memory address, which is in the RAM. Now the reason why this is good is because it's 0 page, it actually doesn't use a lot of memory cycles. So it's a bit quicker, and that's the beauty of that. So this program will read that out, and then it won't do anything with it. It'll just increment y. It'll say, is y equal to 1f? If it isn't, we're going to branch back and we're going to do that again. So it's going to be the value in 0200 with the offset of 1. So this time 0201, and then go through it again. So it's exactly the same as we had here, except we're just looking this time through the RAM, just to make sure the RAM is working. And then if we get to 1f, then we don't branch, we go directly to the break. And remember what happened when the program went into the break routine. We go into that routine we saw before. So this is the software for the Peritech logic analyzer. And the good thing with this software is what you can do is group channels into a bus. So obviously if you were looking here, we've got the address channels, and on their own you really couldn't do much with this. You can't look at 16 channels and see what it's doing, but you can close them like that and you can group them, and then it will tell you in hex what the value is that those channels have created. And obviously that's exactly what we want and how we looked at it when we did the Arduino test. And it's also how we programmed it. So we know exactly what to expect to see, and we just want to make sure that this is going to tell us the same thing. Now this is a bit graphical. We can export this, and we'll see in a minute how an exported version can be played around with as well. But it's useful to see this here on screen. You can see if everything's working fine. Now a few things to look at here is, yes, we've got our reset vector, which is FFFC, FFFD. We've got 00 going in there and F8, so that's all looking good. It then picks up the F800 as our start address of the program. The program starts with A0 on the data line, so we're good. Everything's working just right. One thing to bear in mind is we've got the clock being used here, and this clock is our slow clock. It's not a linear clock, as we can see here. So it's only got a small area here where it goes low and then it's high for a lot longer. That's just how that circuit was generated. So just whatever specific capacitors and resistors we're using will create that. Interestingly, notice that the CPU, the 6502, triggers on the low of the clock, not the high. And I may have been misleading in that last video, that it might have been triggered on the high, but it is actually the low that is triggering us. So that agrees with the fast clock enable that we had in the last episode. So while it's interesting seeing this going at a slow pace, it doesn't tell us anything really different from what we saw before. I stopped it quite early on because obviously this was only doing 2 blips a second, so it took a while. So next would be to look at the fast version and see what differences we've got. Now there's a good website called the Visual Guide to 65XX CPU Timing, and what that does is that steps through how to read a datasheet of the 6502 and the clock timing, actually any datasheet of a CPU, because there are certain timing signals that have to be adhered to, and they give those in the datasheet as to what the length of time for these specific items. So this steps through what it all means, and then the practical implications of that. And something that we see here is that for our particular clock that we've got, there are certain times that we need to wait before we get valid data or we can do anything with it. And what that means is that obviously if we get too close to that, if we increase the clock speed, then the item that we're interfacing with, so let's say we need to interface with a ROM chip as we're doing, the ROM chip might take a certain amount of time before it can put valid data out to the CPU. And if it's probably gonna be around that period here, which in this case is saying around 350 nanoseconds. And so if our frequency or period is encroaching on that area, we're not going to be able to get anything sensible out of it. And we'll have a look at the implications on that when we increase the speed on our version. So take a look at this website. It's really useful to understand the various aspects of timing on these CPUs. So this is the same as we saw before. It's the address lines and data lines of our test circuit with the logic analyzer. But this time, this is at 1 megahertz. So it's looking similar. We start off with our FFFC, FFFD, and we've got 00 here and F8, so that's good. So we're picking out the correct address. And if you look at the address line, it's pretty good. We're not seeing any oddities there. It's pretty stable. But one thing you would notice is if we look at the data lines, we see these items here which we've not seen before. And when I first did this, I thought there might be something wrong with the circuit or something wrong with the logic analyzer. But after questioning the community on Facebook, I'm learning that actually this is a typical way that a circuit will operate when you're interfacing with RAM chips or ROM chips or any memory, that you have to wait a certain period before you get sensible data on the data bus. And it goes back to what we saw before about that line which you can't really go below. And I think if you look at this, we're seeing here, this is around 650 nanoseconds. So this period here you could say would be around 250 maybe maximum. So after 250 you've always got some valid data on that data bus. And that's pretty much all we need. So that's why this circuit is working just fine. But we do see that it's not as stable as we'd otherwise seen before. But I think this is just real world issues. And obviously when we implement that in FPGA, we're not going to have anything like that either. So, you know, we don't have to worry about noise or whatever. But whether this is due to just the chips we're using or circuitry or whatever, it's something that is genuine and actually happening. So we have to factor that in our circuit. In terms of what's happening on the actual circuit, what I've done is I've exported all of this so we don't have to look at it in a line into an Excel spreadsheet. And so we can have a look at that Excel spreadsheet and just make sure that the circuit is doing everything that we expect it to be. Okay, so this Excel file is the output from the logic analyzer. Now, I've had to play around with this file a fair bit because the data packets for the address lines were much neater than the data lines. You'll remember there were a few bits in the early part of the data where the ROM file had to settle down to output the correct data. So I've had to throw away some of those parts and just match them up, which isn't a massive problem, but it's just a bit of extra work compared to the slow version where it all lines up really well. So just a quick run through, we've seen the first part before, so FFFC, FFFD, we're getting our F800 and that jumps us to F800. I've highlighted in blue where we're looking up in the screen area of the ROM. So we start with FB00 and we're reading 0 and then we're writing it to the 0200 area, and I've highlighted that in yellow and orange. So all looks as we'd expect. The first one we actually get anything useful is FB03, which we read 10, and we write that to 0203. So we remember all of that stuff. If we then forward on to 09, we had FB09, we were reading C2, and we wrote that to 0209 C2. So if we jump down to the second part of the program, we go through and we are doing just a read from the RAM now. So the reason why we're doing this read from the RAM is we want to make sure that the RAM has actually taken that information and it's stored it. Whereas before it wasn't going to do that because the RAM wasn't there. So as you saw, we set up our 0 page. So in 00 we put 00, and 0001 we put 02. So that gives us our pointer to memory address 0200, and we're just going to read from that pointer. So we have highlighted in blue the values so we can see them easier. So 00, the first one of use we expect to be 0203, and sure enough we have our 10, 0209 is the next one, C2, then we've got 020B is C4. So as you can see, we are indeed reading exactly what we should have from the RAM. So we've managed to write to the RAM, and now we're checking the RAM and it's checking out fine. And the good thing is this is all happening at 1 megahertz, and we've managed to show that with a logic analyzer. We can now chuck this back into our main circuit and be quite confident that it's going to carry on working at that speed of 1 megahertz and be transferring data from the CPU to the ROM and RAM. We're going to have to be a little bit careful because the Final Tank Battalion game actually has 6 RAM chips and it's got 4 ROM chips. And so as we add those, noise is likely to increase on the circuit. And so we just need to make sure that that's all going to be happy to function together. And the best way to do that is to just incrementally add it and keep checking. So we'll see as we go along with the project that that's all good. So for the Verilog side of things, we're going to do another Modelsim simulation. And we're going to add RAM to our files that we had before. So we're reading from the ROM, writing it to the RAM, and then we can read back from the RAM as we've done in our hardware. So on the GitHub, if we're in Modelsim, these are the files. Most of the files are the same as before. We have the arlet CPU files. So we have the CPU, the arlet6502V wrapper, and the ALU. You'll remember the clock.v, the rom.v, the tank B CPU test, and the TTL chips. This time what we've done is we've added RAM, and we've also changed the file that we're going to read. Instead of screen rom read.txt, it's screen rom ram read.txt. So first, if we take a look at the RAM file, now what I've done here is implemented 2 different kinds of RAM. We've got a single port RAM and a dual port RAM. Now the difference here is that for a typical RAM chip, it's got a single port. So read the data in and the data out is the same port as is the address. And that works fine for normal hardware where you're timing it right between the CPU reading it or writing to it and maybe something else reading it or writing to it. In our test here, that's going to be just fine because we're only using the CPU to either read it or write to it. But later on with our Tank Battalion game, we're going to be using RAM for screen memory. And we're going to have, if you'll remember back to the block diagram we had of the system, we've got the CPU needs to write to the screen memory to change what's on the screen, but also the display system needs to be reading the screen memory all the time too. to be able to show whatever's in that screen memory on the screen. And so a simple way to get around that in Verilog is to create a dual port memory, and we don't then need to worry about the timing between the CPU reading to it or writing from it and then the screen memory, the screen display system reading from it. So we'll see that a bit more in future episodes. Right now I've just put it in here for reference, and we'll just talk about it just briefly. But the RAM file is very similar to the ROM. We've got an 8-bit wide data input, an 11-bit wide address input. We've got a write enable input, a clock input, and we've got an output for data queue, which is also 8 bits wide. And this is mimicking the 2114 static RAM chip. So the first thing we do here is we set up a register very similar to the ROM file that's just 2K in size, and it's an array that's got 8 bits wide. We're setting up an intermediate register for the address, and then we've got a choice here for how we initialize our RAM. Now option 0 is to just leave it. You can just set up the array just without filling it, which might work. You can do option 1, which is just fill it with zeros, which is a safe way of doing it. And then option 2 is, instead of doing this, we could comment that out and do option 2 instead, which is just reading a memory file exactly like we did with the ROM to fill the RAM file. Now sometimes you might want to do that. There's another test we're going to do in a later episode where we're going to fill the RAM with some specific values just to help us with debugging. So you might want to do that. In this case, we're just going to fill it with zeros. Then we go down to the main meat of the actual module, very similar to the ROM file, except this time all we're going to do is we're going to add what happens if we have a write enable. So one thing to mention is typically the write enable was 1 for writing and 0 for not writing. I've made the opposite here with the exclamation mark, so we are writing on a 0 of write enable, just to mimic what a chip would do. As we know, it's write enable low, so I've done it that way. If we had a write enable low, then the RAM at the address that is input equals the data input, and then we have the address register equals the address. And then after that we have our output, whether we have write enable or not, and our output Q is equal to the RAM variable at the address register. So that's fine. For the dual port RAM, it's exactly the same, except for both sides we've got an A and a B. So we've got a data A and a data B, an address A and address B, and write address A, write address B, and also Q out A, Q out B. And it's the same here for setting it up, and then really we're just duplicating port A and port B of what we've already seen, but it allows us to access that same array here with just 2 different ways to it, through either stream A or stream B, and then that'll be able to be used either by the CPU or display circuitry when we get to that point. Next we look at tank B CPU test.v. We've had to make a small change there. We are implementing obviously the RAM, so we've got this module here. That's just instantiating that module. So we've got our data, address, write enable, clock, and queue. So we're saying that the data input to this chip is our CPU data out, which is logical. Our address input is our address line from the CPU, which is A10 down to 0. Our write enable is going to be our write, read, write from the CPU. Our clock is our fast clock, because we're kind of mimicking the asynchronous chip, even though it is synchronous. From the RAM is this RAM data out, so I've created a RAM data out entity there that's 8 bits wide. And then when we go down to our glue logic here, our addressing, you remember we had this one for the ROM before. It was saying that ROM chip select is high if A15 is high. So anything 32K or above makes it high. So we wanted the opposite for the RAM. So the wire RAM chip select, if A15 is low, then the RAM chip select is high. And then all we do is we add this item to our assigning. So this is the CPU data in. So that's the actual data in. Which one does it choose on the data bus? Well, if its ROM chip select is high, then it's ROM data out. And if the RAM chip select is high, then it's the RAM data out. And if it's neither of those two, it's just a default value of 0, 0. But hopefully that never happens, because either of these will be true. And that's the only change to that file, so it's a pretty simple change. So I'm in Modelsim, and I've created a new project for the Tank B CPU test, this time with RAM. So as I did in previous episodes, I've loaded all the files in, I've compiled them all, and then we want to simulate. So I will launch the simulation and I will choose all of the waveforms and then plot them. Okay, so they're all chosen, and then I can run on about 30 nanoseconds and we'll see what we get as the output. So as we got before, you'll remember we had our FFFC, FFFD, and then it starts running the program from F8 onwards. And we can skip along to where we start to read from the RAM. We're writing to the RAM here in 200. But if we skip along to where we're starting to read the RAM. So here's the second part of our program. You remember we look in the 0 page area to 000 and 0001, and we get 20, and then we go to that address 0200, and we expect to find CPU data in. So we're reading from the RAM is here, RAM data out is 0, and that's going into the chip of 0. So that's what we expect at 0200. We remember that we won't get anything until we go to 0203, so we move to there. So 0203, we expected to read 10 out of the RAM, and that's exactly what we get. And then we're going up to 209. At 209, we get C2 being read into the CPU. That's coming from the RAM, C2. So you can see that's exactly what we'd expect. So our demonstration model in Verilog seems to be working just fine. No real point looking further into this. If you want to run this, just download the files off the GitHub, stick it into Modelsim, and you'll get the same as this. You can play around by putting in your own assembler code and maybe, doing read and writes how you want, and just check that it's doing what you'd expect it to do. But pretty much here we've got a functioning system with our Arlet CPU, 6502 CPU, that's got RAM and ROM. It's reading from those, it's writing to those, so we've got a good functioning system. So the next thing we need to do, what we'll be able to do is chuck this back into our main breadboard with the video display, and we can write from ROM into some RAM that can be set as a screen memory. And that's when we really get going with the system working properly as it should as a video game. Because obviously the main part of that video game is writing to screen memory by the CPU. So that's the next one we're going to do.